formation.
Hello, can you guys hear me? Okay. They don't make women's clothes that are friendly to these mics, I will say that. But I even wore pockets today. I'm really proud of myself. So thank you, Michael, for that wonderful talk. And what I'm going to talk about are the low mass extremes of galaxy formations. So we're going to put the ultra and ultra diffuse and the ultra and ultra faint over the course of this talk. What I want to point out is that I will be featuring work from two most excellent graduate students who are here at this conference, so please take advantage with talking with them, and in particular talk with Anna. She's going on the job market, and anybody would be lucky to have her as a postdoc. And this work was not done in a vacuum. This was done in collaboration with the N-Body Shop, in particular Allison Brooks and Charlotte Christensen. Okay, got it. Okay, good. All right, so the structure of this talk goes through 3 different simulations that are all housed within the N-Body Shop. We're going to start with what I call the marvelous dwarf galaxies. We're going to move on to the DC Justice League, and we're going to end with discussing the Romulus simulations. And so this talk is structured from our highest resolution to our lowest resolution simulations, moving up in scale. So here in the marvelous dwarfs, we're focusing on very isolated dwarf galaxies, 4 volumes of these dwarf galaxies, all specifically zoomed in on to be very isolated, many megaparsecs away from a massive companion. The DC Justice League is focusing on dwarf galaxies in an enriched, enhanced environment around a Milky Way. So each of the 4 Supreme Court justices represents our Milky Way. And finally, we're going to talk about what we've heard a lot about, the Romulus simulation. And the questions that I'm going to hopefully answer for you are, what can we learn about the abundance of ultra-faint galaxies using these 2 simulations, or Zoom simulations? And then using Romulus, I'm going to definitely talk about ultra-diffuse galaxies, in particular as satellites and in the field. And this is Anna's work. And if I have time, I'm going to talk about how environment affects satellite distributions in Milky Way analogs drawn from the Romulus simulations. So all of these simulations were run with Gasoline's big sister, Chang'e. Chang'e is massively parallel, which is why it's beautiful for running things like the Romulus cluster, for running the Romulus 25 volume, and why we can achieve such great spatial resolution in our Zoom simulations. We have some great subgrid physics that I'm not going to get into, and we've upgraded our SPH simulation. And as promised, I'm going to begin with the marvelous dwarf galaxies. So these are 4 volumes, each named after a woman Marvel Universe superhero. And these have some fantastic resolution with our star particles a few hundred solar masses. And if you were to convert this to an effective grid, that corresponds to 4096 cubed. And from these 4 volumes, we have 64 resolved dwarf galaxies all the way down to the ultra-faint dwarf galaxy mass scale. All right, so the production runs, which I'm supposed to publish like really soon, are run with a molecular hydrogen-based star formation prescription, and they also include the natural free-range formation of black holes implemented by Michael Tremmel. Unfortunately, I am not going to talk about the black holes in dwarf galaxies, but you can read all about that in Jillian Bellaveri's paper that came out late last year. And actually, what I'm going to focus in on is Captain Marvel, because I had a little bit of fun with Captain Marvel. So we're probing down with the stellar masses of our particles into the ultra-faint range. And the ultra-faint range is a place we've never been before as simulators. And it's scary, and we don't understand things as well as we should. So I thought I'd run an experiment, okay? So I ran Captain Marvel with a simple high-density threshold for star formation. So if you are very dense, 1,000 AMU per cc, and you're very cold, then you, gas particle, you turn into a star. So that is what I call the MC run. Then we have our molecular hydrogen-based star formation, which relies on the gas fraction of H2 if you're a gas particle, in addition to the environment, the metallicity, to be able to turn into a star. So why did I do this experiment? What did I find? It turns out that things look different, okay? And so we heard a little bit about this from Oscar, but if you take a look at these two outputs, the density run versus the molecular hydrogen run in halo mass to stellar mass halo mass to stellar mass space, okay? And you compare them to various abundance matching semi-empirical model results, you'll notice something different, okay? So the results of the simulation are the different points. Circles are centrals, stars are satellites, and they're color-coded by V-band magnitude. And anything below -7-ish is an ultra-faint according to its V-band magnitude. And what you'll notice is that these stars, which correspond to satellites around these dwarf galaxies, and our ultra-faints, those populations look different between the two star formation models. You form 5 times as many ultra-faints in your density threshold run when you compare that to the molecular hydrogen run. So why should you care? That's a really good question. This sounds like a theorist experiment, whatever, who cares? Turns out that if you want to use these simulations to make any sort of predictions that might inform future observations, this matters, okay? So what I've done here is I've produced mock stellar mass functions based on these two runs, okay? And so how I did this was I said, we have an occupation fraction of halos that is different in these two runs, and I can assume a stellar mass to halo mass relationship and an intrinsic scatter on the faint end. We use the scatter discussed in Shea, Garrison, Kimmel's 2016 paper, I believe. And if you stochastically populate thousands of halos based on those 3 criteria, you end up with these stellar mass functions. And so what we have here in green is if you use H2 star formation, and in blue, if you use the metal cooling star formation, and the orange is if you assume a different stellar mass to halo mass relationship. But what you can see is that the predictions you make in this gray shaded region, which corresponds to the DES discovery space, are very different in terms of numbers that you would predict, but simply because I adopted some new star formation model, okay? So what other predictions might this affect? This might also affect how many satellites you would predict around dwarf galaxies in the local volume. Okay? And this is something we care about because, you know, as we discover ultra-faints in our halo, we are figuring out that some of them fell in as satellites around other things. So understanding satellite distributions around isolated dwarf galaxies is something we should care about. And so if you assume our molecular hydrogen run, there's not much of a chance, a 17% chance, that an isolated classical dwarf would have a little friend in orbit around it. However, if you look at the molecular hydrogen run, or sorry, the metal cooling run, the high density run, there's a 50% chance-ish that your classical dwarf should have a friend around it. And if you're looking for more than one friend, unless you believe metal cooling, you got no shot, okay? And so again, these predictions are highly dependent on your knobs. And we learned a lot about this from Oscar earlier on. So why haven't simulators worried about this before, right? Many of you have been coming for many years, and many of us dwarf theorists have gotten up in front of you and said, we make fantastic dwarfs, we're the best, believe us, we've got it all figured out, okay? And the reason it hasn't been a problem before is because at classical dwarf scales and above, galaxies can self-regulate. And this has been shown by some really talented people, including Samantha Benincasa, who is here. And what she did was she tweaked some of the knobs that we can tweak in our simulations and showed that on average, the ISM pressure doesn't change even if we're tweaking things by orders of magnitude. And Charlotte Christensen has shown this on a dwarf mass scale where she's tweaked star formation, and the outflow to star formation rate ratio doesn't change much over time and in between these models. So what's going on is that star formation and feedback can self-regulate in classical dwarfs and above, but they absolutely cannot in ultra-faint galaxies. And so you might be wondering, why is there a difference? And what we found in our little Captain Marvel experiment is that it turns out that the culprit is metallicity. So metallicity, go sit in a corner, wear a dunce cap, because as metallicity decreases in your molecular hydrogen run, the star formation is pushed to higher density material, because without those metals, you don't have the dust, you can't facilitate H2 formation, but in super, super high densities, you can sometimes make some molecular hydrogen. And you can see that here in this phase diagram. So we have log of density on this axis, and we have temperature on this axis. The light gray points are the metal cooling high density run, and then the black points with the contours show the molecular hydrogen run, and this is for star formation in the first giga-year of the simulation when ultrafaints are assembling. And what you can see is that that star formation in the molecular hydrogen run is relegated to that high-density material. So as a result, in that run, it is increasingly difficult to form many, if any, stars before reionization gets you. So take-home point, just to reiterate, is classical dwarfs self-regulate. So these prescription things don't matter in the way that they matter at the ultra-faint regime. So the other thing that Oscar advertised that I talked to you about is actually really hot off the presses. So this is stuff that I've only been thinking about this summer, mostly in the last couple of weeks. So I'm happy to hear input and ideas from you guys when we get to questions. So what I'm showing you here is a function of halo mass, is the number of halos that host a galaxy over the total number of halos in that mass bin. And so what you can see, as expected, at higher masses, we're forming galaxies, galaxy formation efficiencies up there at 100%, but it decreases down at lower halo masses where everything is pretty much dark by about 10 to the 7-ish solar masses in halo mass, okay? You know, when I was a naive grad student, I always pictured this galaxy formation efficiency to look like a step function, where you're forming your galaxies, your halos can do it, and then they can't. And so what we're seeing here is something a lot more gradual, but what's notably interesting here, there are two things that are notably interesting here, is one, that there's a spread in what our 4 volumes predict for how galaxy formation efficiency decreases as a function of mass. And also, that even at masses where we think that those halos should be occupied, we're still getting these dark halos, okay? Frank is making a scary face about this. And I actually spent some time last night and made my grad student do more work than he probably wanted to do. But I've looked into some of these dark halos. I can't talk about them during this talk, but come and talk to me about them if you're interested. So why am I making a big fuss about these occupation fractions? Well, occupation fractions matter when you want to make predictions for observers. Okay? So what I did here was I took a mean occupation fraction for all 4 Marvel volumes. Okay, and then I assumed a stellar mass to halo mass relationship and intrinsic scatter to that relationship and populated mass functions. So this blue one is the high density threshold star formation model that I talked about before, and in green and orange are, if you use that mean occupation fraction that you derived from the marvelous dwarf galaxies and 2 different stellar mass to halo mass relationships, what you'd predict for the faint end of the stellar mass function. And you can see that these predictions are different in terms of numbers of ultrafaints you'd expect to find, say, in DES. Okay? So the point is, yes, slope and scatter in the stellar mass halo mass relationship is important, but the occupation fraction you predict in your simulation is just as important. Whoops. And so just to show this clearly, I'm using the most dramatic blue occupation fraction and comparing it to this purple occupation fraction, which is more gradual, and predicting stellar mass functions. And what you can see is even between the 4 volumes that were selected with the same criteria in mind, that have the same star formation physics, the occupation fraction matters, and you predict very different number counts of ultrafaints in the DES discovery phase. So again, occupation fraction matters. So we've got to figure out, what's going on here. So I've painted a very bleak picture, okay? I've said ultrafaints can't self-regulate. How I turn my knobs matters. So what can simulators actually do for you? It turns out that when you move away from isolation into an enriched environment, the picture is not so bleak. So this is where the DC Justice League comes in handy. Each Milky Way that we've simulated is named after a woman Supreme Court justice, thus the Justice League, and terrible Photoshop. And what I want to point out is that 2 of the 4 Milky Ways have been run at the equivalent resolution as the marvelous dwarfs. And so as a result, we are able to resolve ultrafaints in this more dense environment, in this pre-enriched environment. And so while different star formation physics predicts different things in isolation in Marvel, it turns out there's very little difference between star formation prescriptions in these dense environments. And I've been saying this is due to pre-enrichment. These halos can get enriched because they're in that dense environment. And so this is work that is being led by Elad Applebaum, who is here. If you haven't talked to him, you should. And what I'm showing here as a function of halo mass is number of galaxies and how they're pretty much consistent between the metal cooling run, the high density run in green, and the H2 run in blue. So you might be wondering, how then can an observer help a simulator constrain star formation in these ultrafaints if in these enriched environments everything kind of looks the same? Okay. This is very preliminary, but what Elad has found was that it turns out that instead of being put in the corner, metallicity should be brought back out, because metallicity might be the answer here, okay? So if you look at the metallicity distribution functions for matched ultrafaints between the high density run and the molecular hydrogen run, it turns out that the high density run has a wider metallicity distribution function that peaks at lower metallicities, whereas the H2 run has a narrower metallicity distribution function that peaks at higher metallicities. So Evan Kirby's stacking work on metallicity distribution functions of ultrafaints might be really insightful for simulators to figure out what they're doing. And these distributions may point us to the conditions of star formation in the early universe. So I just want to say, between Marvel and the Justice League, we have 165 simulated high-resolution dwarfs. If this doesn't impress you, I got nothing. But if you ever want simulated dwarfs, the N-Body Shop got you. So come and talk to me if you need some simulated dwarfs. And in my last few minutes, I want to advertise Anna Wright and her work on Romulus in studying ultra-diffuse galaxies, in particular in isolation and as satellites. So this is using the Romulus 25 volume, which is just like same physics as what Michael just talked about in the cluster, but instead of a cluster, it's a volume. And Anna is the queen of the low surface brightness universe. And in particular, she's identified over 570 isolated low surface brightness galaxies, which comprise 50% of the population in the box. And while at redshift 0, they look like they might have higher spin, it turns out that that's not true when they form. And so please talk to her about her LSB work. It's fantastic. And I just don't have the time to talk it up, because what I want to talk about is actually more work by Anna. I've never seen such a productive grad student. Basically looking at a subset of our LSB universe, which are UDGs, okay? And so as Michael said, consistently with the cluster, the UDGs in isolation and in Satellites are all dwarfs in terms of their halo masses, in terms of their stellar masses, and what their baryons look like. But I want to point out that we've created the first statistical sample of simulated UDGs across the environment. We've got Michael's cluster UDGs, we've got isolated UDGs, we've got satellite UDGs, and we have over 500 UDGs. Okay? And just really quickly, in my last minute, I'm just going to throw up one of Anna's results. She found that high mass UDGs in isolation are UDGs simply because they're faint, okay? And low mass UDGs in isolation are UDGs because they're large. And neither of these things has anything to do with spin and angular momentum. None of these things can be explained by elevated angular momentum, and that's what she's showing in these figures here. So now he's standing up. And so I'll skip through a couple of slides, but I have some really interesting environmental dependence of satellites and Milky Ways that come from Romulus, so please talk to me about that. And with that, I will end by saying I love all the small things. We have a fantastic suite of simulation that gives us all the small things. And so with the exquisite resolution in Marvel and the DC Justice League, we're really trying to nail down what's going on with ultrafaints, what's going on in the really low mass end of the stellar mass-halo mass relationship, and we want to make robust predictions for surveys like LSST and DES. And with the statistics and resolution of Romulus, we've got numbers, okay? And so we're doing that to study the statistics of dwarf galaxies, satellite distributions around Milky Ways, and Anna's fantastic work on ultra-diffuse galaxies. And so with that, I'd be glad to take questions.
Questions?
So judging from the fact that you see so much scatter between each of the Marvelous runs on the low mass end of the halo mass function, how big of a volume or how large of a number of objects in isolation would you have to get to actually have a reasonable measure on the sigma of that relation, do you think?
That's a good question. And when you were asking that question, the first thing I thought was that no matter how big the volume, your resolution is going to be your limitation, because it's going to put a floor on the lowest mass galaxy that you can resolve. And so I think before we can attack it volume-wise, we have to attack it resolution-wise to really get a handle on how that scatter grows. And so one thing that we've thought about doing is, what happens if when you calculate scatter, you throw in as kind of like just because you have them, how many dark halos you have at a given halo mass, and blow up the scatter in that way and put kind of an extreme bound on the scatter. But different people have different feelings about that.
More questions? No? Okay.
Michael, you can ask me questions anytime.
Yeah, I know, but so could Ben. Anyway, so I'm wondering the difference between the H2 runs and the pure density threshold runs. Mm-hmm. Could that be alleviated just simply by pushing the density threshold higher on the density threshold runs, or is that not? I mean, obviously for the metallicity content, that's a whole different story, but
right.
For the isolated galaxies, do you have any idea?
I think that would mess with your stellar masses then. You wouldn't be forming sufficient stellar mass to match, say, the stellar mass-halo mass relationship, because both of these are in pretty good agreement with stellar mass to halo mass relationship.
Okay. Quick question.
Just curious whether you ever looked at what your simulations predict for the H1 gas mass fractions of UDGs and the other dwarf galaxies.
We have, and Anna can show you those figures.
Yeah. Okay, so thank you, Ferah. Let's thank Ferah again. And let's go for coffee, I guess.